All right, this is the first online lecture for Math 403. So this is Chapter 12, which introduces the topic of rings. So a little note here, rings are going to basically take up the rest of the semester. This is sort of basically how the course is divided. And so basically, by way of intro, let me give you a little intro. And so for the record, I'm basically following the lecture notes that I wrote, which are online, and I'll probably just sort of throw in some more stuff and draw it out a bit. And because very often there are things that I think of when I'm teaching that I don't think about when I type the lecture notes. So the basic idea here is that for a group, we get one operation. This we know. One operation. Usually it's addition or multiplication or composition of elements or something. So for a ring, we basically put in another one. Now this may seem, let's say, two operations. This may seem like it's a very small step because we might be like, well, you know, just two isn't much more than one. But what happens is once we have two operations, basically it like cracks things open and we get, you know, multiple. So for example, even when we have one, when we have addition, we basically get subtraction because we get inverses. So arguably, if you have like addition and multiplication, maybe you get subtraction and maybe you get division, and then you could maybe get exponents and so on. So by structurally beginning with two operations, it sort of gets a little more complicated than that, right? So let's say 2 is enough for lots of stuff. So formal definition. So a ring R, so it's a set. It begins sort of like a group. It's a set, but in this case we're going to have with two closed binary operations. So remember, closed means you combine them and you get something in the set. Binary means you combine two of them. So we'll denote these. So let's say this given A and B in R, we have A plus B in R and AB in R. So for the record, the two operations don't have to formally be addition and multiplication, but in every single case we will ever look at, those will be it, right? So we'll always have addition and multiplication. So yeah. So there won't be any ambiguity. Like with groups, there's sometimes ambiguity. For rings there really isn't, at least for us. So it's a set with two closed binary operations such that the following hold. So these are requirements to have a ring. First requirement is that A plus B equals B plus A. In other words, addition is commutative. B, A plus B plus C is A plus B plus C. So addition is associative. There's an additive identity. Which we'll say denoted 0, D. There are additive inverses. And so we'll sort of use a standard here. We'll write negative A as the additive inverse of A. And we'll write say A minus B to mean A plus the additive inverse of B. So this should all make good sense, in a sense. But, you know, here's an example. So we've got addition, and now we've automatically got subtraction. It's not really a new operation per se. E. Multiplication is associative. AB times C is A times B times C. And multiplication distributes over addition. So A times B plus C is AB plus AC, and also coupled with that, B plus C times A is BA plus CA. So a couple things that I want to make here, a couple notes. So first note is basically a ring is an abelian group under addition, which gets an additional operation. So basically a ring is an abelian group under addition. In which we also have multiplication. Now, some important points here. That there's no reason for the multiplication to be commutative. Notice that's not a requirement. That's none of A through F. All right, so in other words, i.e. AB does not necessarily equal BA. So third point, there's no guarantee of a multiplicative identity. Now, if there is one, it has a name. It's called a unity. We'll see examples of all these very, very soon. If there is a unity, there's no guarantee of multiplicative inverses. So if there exists a unity, there's no guarantee of multiplicative inverses. And that basically summed it all up. Let me think, is there anything else I wanted to mention? Oh, okay, so the last thing that goes with this, that if an element does have a multiplicative inverse, it's called a unit. So what I'll do next is, one last note, actually, and then we'll be good. So a couple of notation notes. So for A in R, we write A to the N to mean A dot 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 A N times. And NA to mean A plus dot 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 plus A N times. And if there's ever any ambiguity between NA thinking that it's like 3 times A versus like 3 times A in the ring, then we'll clarify. So what I'll do next is let me just run through a few examples of these so we can see, especially some of these bullet points, like what can and cannot happen. So, for example, the integers z is a commutative ring. With a unity. 1. So remember, that means that 1 is a multiplicative identity. One times anything is the anything, and units plus or minus 1. So that means plus or minus 1 are the only things with multiplicative inverses that you can multiply by to give you 1, right? So i.e. 1 is a unity because 1 times, let's say, a is a, which is a times 1 for all a in Z, and plus or minus 1 are units because 1 times 1 is 1, which is the unity, and negative 1 times negative 1 is 1, which is the unity. So in other words, each of plus or minus 1 has a multiplicative inverse that you multiply it by to get you the unity. So second example, Zn. This is a commutative ring with unity. One and unit u of n. This may not be so obvious, this second part, right? The fact that the unity is 1 is pretty clear. 1 times anything is the thing. But the reason why u sub n is basically the set of units. So what this means is, i.e. if a is in un, this means that the GCD of a and n is 1, which means that a has a multiplicative inverse. Right, there exists a b such that ab equals 1 mod n. This may or may not be so obvious. It's a basic number theory fact, but if it's not so clear right now, that's okay. Next example. So both of these are pretty straightforward so far. So I want to make sure that we see a couple that are maybe not commutative or don't have unities or so on. So 2z, this is the even integers. This is a commutative ring without unity. Right, there's no 1. There's no multiplicative identity. And because there's no unity, there are no units. So next example, GL2R. Remember, this is the set of 2 by 2 matrices with non-zero determinant. This is not a ring. This is because addition is not closed. You can take two things with non-zero determinant and add them and get something with zero determinant, right? So for example, e.g., say 1, 0, 0, 1 plus negative 1, 0, 0, negative 1, right? Both of these guys are in GL2R. This gives us 0, 0, 0, 0, which isn't. So I only mentioned this one just to prove a fact that here is a thing which is a group under multiplication, but isn't a ring with addition and multiplication. All right, related is M2R. This is the set of 2 by 2 matrices. This is a non-commutative ring. With unity 1, 0, 0, 1 and units GL2R. So in this case, GL2R is the set of matrices that do have multiplicative inverses. So that's why the units, right? So i.e. GL2R, these are the guys that have non-zero determinant, hence have multiplicative inverses. And one last one, the quaternions. If you don't know these, that's okay. H This is a non-commutative ring with unity. And all non-zero quaternions are units. Again, we won't see those much. I just wanted to give one that was non-commutative that wasn't the matrices, because those are sort of the standard batch. So now that we have a few, there's some properties that follow from these, or that follow from the basic definition of a ring. So let's say theorem. Let's say properties of rings. So these are properties that don't need to be given in the definition. So if A, B, C, and are in R, oops, not the reals R, but in the ring R, then we have the following. So A, I'm going to make a comment at the end about these, but think about them as I write them. So for example, I'll say the comment as we go. So A times 0 equals 0 times A equals 0. Now, if you stop and you read that superficially, like you read that, like it looks like it makes perfect sense. You're like, well, A times 0 is 0, because you're thinking in the context of like the real numbers. But what this statement is actually saying is that if you take any element in the ring A and you multiply it by the additive identity, you get the additive identity. That's what this is saying. And that's not as obvious, right? So same with the second one, right? A times negative B is negative A times B, which is negative AB. So if you think about what this says, it says that if you multiply A by the additive inverse of B, you get the same thing that you get when you multiply the additive inverse of A by B, which is the same thing that you get when you take the additive inverse of the result you get when you multiply A times B. That's a mouthful there. So C, negative A times negative B is AB. So in other words, minuses cancel. D, A times B minus C is AB minus AC, and B minus C times A is BA minus CA. And then in addition, if R has a unity, so if R has a unity, then we also get E. Negative 1 times A is negative A. And F, negative 1 times negative 1 is 1. So again, I'm going to write this in a second, but keep in mind that these are not as obvious as you think they are, because you're thinking they're obvious typically because you're thinking in terms of real numbers, which these are not necessarily. So again, the point I want to make is these are not obvious. All right, for example, C states that the product of two additive inverses gives you the same as the product of the two elements, right? C states, let's be more specific. If we take A and B and R, find their additive inverses, multiply those, we get the same result as if we multiplied A and B. So again, not so obvious. So proof, let me just prove a couple of these. You should try the ones that we haven't proved. Some of them are in the book, some of them are not in the book. They're all, none of them is particularly difficult, but they're all a bit sneaky. So here's A, for example. So first note that 0 plus A times 0, right? 0 is the additive identity. So this is the same as A0, because 0 doesn't do anything, right? Now, 0 is the same as 0 plus 0, because 0 is the additive identity. This is A times 0 plus 0. Because of distribution, we get A0 plus A0. Right, so let me clarify all these for a second before I do the last step. So this is because 0 is the additive identity. This is because 0 equals 0 plus 0, because of the same reason. And this is because multiplication distribute over addition. So that's why we're allowed to do all that. And then at the end of the day, we just cancel an A0 from both sides. Which we're doing because everything has an additive inverse. So basically cancel this from both sides by adding the additive inverse of A0. So that takes care of A. And then here's the proof of part of B. So again, note that A times negative B plus A times B is A times negative B plus B. That's by sort of the reversive distribution. This is A times 0, and by A, this is just 0. Right, so again, just to break down what happened in all of this, this is by the reverse of distribution. This is because negative B plus B equals 0. That's the definition of negative B, and this is by A. So once we get all that, then what we can say is that look, when I add A times negative B and A times B, I get 0. That means that A times B is the additive inverse of A times negative B. Right. So in other words, let me put it this way: that A times negative B is the additive inverse of A times B. And I got a little overzealous with the parentheses here. So A times negative B is negative AB. QED. So all of the other things in all of the other A through F are similar to this. They're sort of fiddling around with things, and like I absolutely recommend that you try them, give them a go, see which ones make sense, see which ones don't. They're typically pretty challenging because you have to always stop and think about what you know, because the things that you think you know, you generally don't know. Like you're never quite sure, so you have to sort of really get down to the nitty-gritty basics and go from there. So second to last thing is another theorem about uniqueness. And so it basically says the following. It basically says that if a ring has a unity, then the unity is unique. And if an element is in a ring has a multiplicative inverse, then it is unique. So if a ring has a unity, then the unity is unique. And let's say if A in R is a unit, remember that means it has a multiplicative inverse. Then that multiplicative inverse is unique. So the proof of this I'm not going to give. The proof is exactly the same that we used for groups. In other words, in groups we proved that the identity is unique, and we proved that inverses are unique. So it's the exact same proof. So the last thing is about subrings. So two things: a definition and a test. So a subring is a bit like a subgroup, but for a ring. So a subset S of a ring R, oops, not that kind of R, this kind of R, is a subring if it's a ring in and of itself using R's operation. It's a subring of R if it is a ring. Under R's operation. So for example, 2Z is a subring of Z. Or another example would be like R, the real numbers, is a subring of R bracket X, where R bracket X, this is the ring of polynomials with real coefficients. If it's not clear that that's a ring, it's actually a really interesting ring to look at. So give it some thought, think about why it's a ring, think if it's commutative, think if it has a unity, think about what the units may be, etc. But the real numbers is a subring of that. All right, and last but not least, we have Subring Test. Bit like the subgroup test, it says a non-empty subset S of a ring R is a subring of S if for all A and B in S we have A minus B in S, it's a minus in there, and AB in S. So the proof of this I'm going to omit, it's fairly straightforward. That may not seem like it is, but definitely give it a try and see what you can get out of it. So here are two examples. Again, they're examples of subrings, but think about them in terms of the subring test. So for example, NZ, like 2Z, 3Z, 5Z, etc., is a subring of Z. All right, so if you stop and you think about it, if you take two things in NZ and you subtract them, you get something in NZ. If you take two things in NZ and you multiply them, you get something in NZ. And second example, a little less obvious, is the set Z bracket I. So this is a set of A plus BI, where A and B are integers. This is a subring. This is the complex I. Subring of the complex numbers. And again, if you think about it, like, well, if you take two things in here and you subtract them, you'll get something in here, because the coefficients will always be integers. And if you take two things in here and you multiply them, you will get something in here, right? So in other words, if you wanted like a little proof, you could say, well, take A plus BI and C plus DI in ZI, then A plus BI minus C plus DI is A minus C plus B minus DI, which is in ZI. And if you multiply them, there's a little bit more work that needs to be done. So here we get AC minus BD. Oops, let me rewrite that. Because the B times D is with an I squared, so that's a -1. So AC minus BD plus AC let me get that right. AC plus, sorry, no. AD plus BC. I. And that is in ZI. This actually ring we'll look at a lot later, so it's a good one to sort of see the subring for. So that's pretty much it for chapter 12. There we go. That's everything. That's all the basics about rings before we move forward.